Hello friends, this is Tomohiro Oishi. The title of my talk today is Relativistic Energy Density Functional Theory on Daydream of Nuclear Physics. What is the daydream, I said? Actually, this is described by this black box, that is universal theory for a nuclear structure. This black box, if that would be completely established, can reproduce full information on the arbitrary nucleus, including binding energy, charge and matter radii, collective excitation and radioactivity, etc., only from the input parameters of Z and N, namely proton number and neutron number. As one candidate or archetype for this universal theory for nuclear structure, the relativistic energy density functional theory has been developed. So let's remember a little bit about the nuclear physics. What is the target of us? That is atomic nuclei being many body systems of protons and neutrons. And here proton number Z and neutron number N determines the chemical character and isotope. So one natural question arises. Do we know all the properties of all the nuclei? And unfortunately, the answer at this moment should be no. There can be 3,000 to 4,000 nuclei at least in the nature, whereas the precise information is available only on 300 to 500 of them, namely, about 90% of existing nuclei are waiting to be investigated. And now, let me repeat that the universal theory of nuclear structure is one dream of nuclear many-body physics. That is the black box I showed first. And here, physical properties of atomic nuclei to be reproduced include static properties and dynamical properties. The static properties include binding energies, spin and parity, charge radii, matter radii, exotic shapes, pairing gas, magnetic characters, blah blah blah. On the other side, dynamical properties include collective excitation, radioactivity, strong interaction response, and electromagnetic response, weak interaction response, etc. Indeed, as I said, there are too many properties we need to consider. So the goal of this universal theory is, of course, still far away. But, okay, even though the goal is too far, we cannot give up. Indeed, towards this goal, there are several archetypes in the nuclear theory. The first one must be quantum chromodynamics. This is the most fundamental theory to reproduce or describe the strong interacting systems. But unfortunately, QCD is not yet possible to calculate the low energy nuclear properties. Then the next candidate I introduce here is shell model calculations. And also, the other candidates include ab initio calculation as well as chiral effective field theory. For the detail of them, please refer to these papers I list here. Then, as the last candidate, let me introduce energy density functional theory. And actually, this is my main topic now. So the energy density functional theory for atomic nuclei has been utilized as one tool to calculate the nuclear properties. And there are two versions of them, that is, non-relativistic version and relativistic version. The former category includes the Skarm or Goni types, whereas the later, relativistic EDF, includes meson exchange or point coupling models. And implementation of numerical computations based on these EDF theories has been done for the ground state. Then their self-consistent EDF mean field calculation is their famous and typical example. On the other side, for the dynamical properties, let's say, for example, collective excitations, that is, not easy as well as their ground state properties to be reproduced, then, for example, the quasi-particle random phase approximation, or more generally, time-dependent EDF calculations have been utilized. And actually, I'm especially utilizing the relativistic version of nuclear EDF theory. So what can be the advantage to utilize the relativistic framework? And here, let me introduce 3 points. The first one is that in the original work by J.D. Wallecker, who wrote this reference paper number 1, his original motivation was to obtain the stress tensor for the Einstein equation of neutron stars. And for this purpose, it needs the relativistic formalism, because actually having the Lagrangian of many nucleon systems is the most natural way to obtain stress tensor. And then, as a successful result by Wallecker, the repulsive core of the nuclear force in the high-density region can be naturally concluded. The second point is the Dirac-Lorentz formalism. The Dirac-Lorentz formalism leads to a consistent treatment of spin degrees of freedom, as well as an unified description of time-even and time-odd fields of nucleons. Also, the relativistic effect and causality can be naturally included by using the Dirac-Lorentz formalism. Finally, the spin-orbit interaction, which is one fundamental feature of atomic nuclei, is naturally concluded. So let me explain a little bit more for this final point, spin-orbit interaction. What is spin-orbit interaction? This is a kind of two-particle interaction whose potential or Hamiltonian includes the so-called LS product. An LS product is typically formulated as this, including the orbital angular momentum L and spin angular momentum S. And you may ask, why do you take this strange or crazy stuff? And actually, that is important in the atomic and nuclear physics. Here, I'll explain the role of spin-orbit interaction in atomic physics, as well known. To explain the spectrum of atoms, Schrödinger equation is well used, and actually, that equation approximately explains those atomic spectra. That is, this En, where the En is determined by these fine structure constant and masses of electron and atomic nucleus. And this result is not bad. However, in the super accurate measurements of spectra, there is a branching into some levels that is called fine structure. And to explain these fine structure level splitting, we need some corrections in addition to the original Hamiltonian used in the Schrödinger equation above. And here, the Hamiltonian after corrections includes HLS, H Darwin, and T Rela. Those are spin orbit, Darwin, and relativistic correction terms. Also in nuclear physics, spin-orbit interaction plays an important role. Atomic nucleus is the many-body system of protons and neutrons, and for them, magic numbers are well known. Those include 2, 8, 20, 28, blah blah blah. Then, when the number of protons and or neutrons is equal to one of those numbers, that nucleus becomes more stable than other cases. To explain these magic numbers, the spin-orbit interaction plays an essential role in this way. the mean field potential for a single proton or neutron is given as this VR, including the second term, that is spin-orbit interaction term. And actually, Goppert and Mayer and Jensen, who proposed this idea first, got Nobel Prize. Comparing the Schrödinger and Dirac equations, the Schrödinger equation is not bad, but phenomenological corrections are additionally needed to explain something in atomic or nuclear physics. On the other side, by using Dirac equation, one can naturally describe those phenomena. I must skip its details here, but if you are interested in this ability of Dirac equation, actually I uploaded the other video in my channel, so you can see that. Finally, I will show some of my results obtained from the computations based on the nuclear REDF theory. Here, the REDF is originally determined from the Lagrangian I wrote on the right-hand side of this panel. Okay, it looks a little bit complicated, but basically those include isoscalar scalar, isoscalar vector, isobector vector, and blah blah blah, namely those 6 terms. Then, starting from this Lagrangian, I did the mean field approximation, and then some physical properties of atomic nuclei were successfully reproduced. In the left panel, I show the calculated results for 2 neutron separation energy, S2N, the binding energy per nucleon, E over A, and charge radii of calcium isotopes, calculated by the REDF. Here, DDPC1 plus D1S or DDPC1 or S1P indicates one setting of REDF parameters. Comparing those results with experimental data plotted also here, one could read that, okay, the result is not bad, except the charge radii is not reproduced well with respect of the experimental results. But actually, for the binding energy per nucleon and 2 neutron separation energies, it works really well. Then on the right hand panel, I also calculated the photoabsorption cross-section. And actually, that is the physical quantity of reaction when one reacts the atomic nucleus by the gamma ray, for example. Then the atomic nucleus can absorb some gamma ray and as well as its energy, and that can be excited. To explain those excitations, here I calculated the photoabsorption cross-section, which is actually in a good agreement with experimental data. And here upper panel is the result for samarium 144, whereas the lower panel is that for the samarium 154. And in both cases, our REDF calculation roughly reproduces the experimental data. Summary of this talk. So, in the nuclear physics, there is one dream, that is universal theory for nuclear structure. And this theory that would be completely established is able to explain full information on the arbitrary nucleus, including binding energy, charge radii, and matter radii, blah blah blah. But, of course, as I explained, this goal is still far away. Toward this goal, the REDF theory has been in progress, and as well as other candidate theories. And if this kind of universal theory would be established that can benefit these relevant topics, including general energy density functional theory, many body systems with interactions, or to explain origin of elements and materials, stellar evolution, and supernova in astrophysics. Also, for nuclear technology, process of radioactive wastes is the good testing field to utilize this universal theory for nuclear structure. As well, also for information technology, novel device for quantum computing could be developed based on this atomic nuclear physics. And for medical applications, that could be also useful as well as in material sciences. Okay, thank you very much for your attention.